Okay, if you have any questions, please ask. This is probably a good time for me to ask 4 questions. If you have any, just to make sure that we all, all the material that I presented last time was clear. Or maybe if I should slow down. Do you have any questions? Okay, so feel free to ask during the lecture. I will review quickly just some notions with some comments from last time. And also you remember one thing that I mentioned at the beginning was Hausen's theorem. Given a free group, you take 2 subgroups, 2 finitely generated subgroups in this free group. So they have finite rank, then take the intersection of those 2 subgroups. The question is the intersection finitely generated as well? So Hausen's theorem says yes, it is finitely generated. And a good way to prove it is this topological combinatorial point of view due to Stallings. Now it should be reasonably clear why this theorem should be true. Let me say just a few words. So you start, so gamma is a free group, A and B are finitely generated subgroups in gamma. So A and B are free. What is the rank of the intersection? So these are of finite rank. What's the rank of the intersection? What you do, you just build this Stallings diagram. You construct X, and then you construct Y and Z, which represent this inclusion. So pi1 of X again is gamma, pi1 of Y is A, and pi1 of Z is B. So you start with some, we can assume that gamma is finitely generated, right? Just replacing it with the subgroup generated by A and B. There is no loss of generality by doing this. So since gamma is finitely generated, then X can be taken to be a finite graph. And then you represent it by covering, and then you collapse the branches in the covering you take only a finite part of the graph. This is what we call Y. So this map is now not a covering map, but a restriction of a covering map to a subgraph. So it becomes an immersion. This is also an immersion, and every immersion one can check, and this is what is done in Stallings' paper, that immersion induce injective maps on fundamental groups. So this induces an injective map from A to gamma, and this induces the injective map from B to gamma. And then you take the fiber product. S is the fiber product, and the intersection happens to be, again, there is something to check here, but the intersection happens to be pi1 of A component of S. So one would need to do a little bit of work to check this. But then you immediately see that since we took Y and Z to be finite graphs, their fiber product is also finite, because it is defined in terms of Cartesian product. All the edges here, an edge in S, for example, is a pair of edges, 1 and Y, 1 and Z. Right. So the set of edges is a subset formally of the Cartesian product, the set of edges in Y and times the set of edges in Z. Since both are finite, then S is also going to be finite. The same thing for vertices. So S is finite, and in particular any component of S is a finite graph, and the fundamental group of a finite graph is finitely generated. End of proof. So once you kind of restate this in these topological terms, of course, I mean, there is some work involved here. You need to really check all this, and you check that the intersection is indeed the fundamental group of some component. But when it's done, it's immediate that it must be finitely generated. So that's one comment. Another Let me give a formal definition of a Cayley graph, since I didn't give it last time. So a Cayley graph of a group gamma generated by, with respect to a generating set. Say pick a finite generating set. One can do it for infinite generators as well. Pick a finite, for example, generating set. Assume gamma is finitely generated. Then, so what is the graph? Let's call it G. G is defined as follows. So vertices of G are, this set of vertices is just, they are labeled by the elements of the group. This is just G, and this is just the group gamma itself. So each vertex, one-to-one, corresponds to an element of gamma. And then edges you take, pick an element. Edges are labeled by the generators, and whenever you see the following, whenever you see G, some element of gamma, which is a vertex, and you take another vertex which corresponds to G times xi for some I, where xi is one of the generators. So whenever you see such a pair, you connect this pair by an edge, and you direct it from G to gxi, and you label that. So the label of that edge is xi. So whenever you see such a pair, you connect them. Since this is the set of generators, if you pick any two vertices, you can get from one vertex to any other vertex by consecutively multiplying on the right by various xi's. And multiplying by xi inverse means going in the opposite direction. So that's the formal definition of a Cayley graph for any group. But now, in particular, when gamma is free, so when is free, and x1, xn is a basis of gamma, then the corresponding Cayley graph, then G is a tree. So it is connected because x1, xn are generators. And it is a tree because there are no loops in it. So a loop would correspond to a word which is a word in generators which is equal to one in the group. But this never happens in a free group, so there are no loops. So it is a tree. That's one definition that I didn't state explicitly last time. And we talked about trees. So a tree, you remember, I drew this picture. Something like this. It's a graph that has no loops. A flower was a graph homotopy equivalent to a circle. A circle maybe with a bunch of branches attached. But then one can combine this, right? These are the connected graphs. One can allow disconnected graphs, and by which I mean one could take a graph whose components are these or these, and that's natural to call a garden. So a garden is like a picture of a bunch of trees and a bunch of flowers, right? You have some kind of trees here. Here's a tree and here is a flower. And maybe several of them, right? Something like this. So this is a garden. So a garden is it's a graph whose components are either trees or flowers. And why? I mean, why does this deserve a certain a name? Because that's exactly so a graph. Let's say a finite graph. Let's deal with finite graphs. A finite graph, let's call it, say, y. is a garden if and only if the reduced rank of y is 0. So it has this nice characterization. It's why it deserves a special name, because that's such graphs are exactly those which have reduced rank 0. That's a little exercise to check. And we obtained essential sets of edges. You remember, you start with any graph y, maybe not a garden, just any. Doesn't have to be connected. Let's say finite graph, and then you pick an edge such that removing this edge strictly decreases the reduced rank. Then you pick another edge that again decreases the reduced rank, and you continue doing this. You make sure that at each step you strictly decrease the reduced rank by 1. And you stop exactly when the reduced rank becomes 0. But it becomes 0 exactly when your graph is a garden. So say, one could take, let's take this example, say a graph like this. It has 3 circles connected to each other. So what would be a maximal essential set? It's not uniquely determined, right? There are many choices of maximal essential sets. Let's try to find at least maybe 2 choices. So say I could pick an edge here somewhere and remove that from the graph. Right, that would so what is the reduced rank, first of all, of this graph? The usual rank is 3, so the reduced rank would be 2. So we know that in a maximal essential set there will be 2 edges. Say this edge you remove, and what else could we remove? We could remove, for example, an edge somewhere here. The rest, after you remove those 2 edges, what is the rest? This becomes a branch. The only thing which is kind of non-trivial here is the circle. So it's a circle together with a branch. So it is a flower. But I could also do the same thing, but also could choose a maximal essential set in a different way. I could, for example, remove an edge somewhere here inside. Removing this, again, we started with the reduced rank 2. Removing this edge, what will happen? This becomes a flower, this component, and this component has a reduced rank what? 1. The reduced rank is 1. So the total reduced rank would be what? 0 plus 1 is 1. And then remove another edge. For example, I could pick again another edge somewhere here inside, and I remove that. So those 2 edges would be an example of a maximal essential set. The difference between the previous example is that after removing the 2 edges, the graph was connected. It was a flower. In here, we had 3 flowers, but it still doesn't matter because the reduced rank of each of them is still 0, right? So the graph doesn't have to be connected after you remove. This is the difference between choosing a maximal subtree, the usual construction of finding a basis for a free group. You represent it as a graph, and then you find a maximal subtree in a graph. Since you find a maximal subtree, it means that you're looking for a connected tree, right? Tree by definition must be connected. And the graph you started with also should be connected. In here, connectedness doesn't really play any role. You're not looking for a maximal subtree. You're looking for a maximal. So find. This is equivalent. So this is equivalent to finding what? Finding the usual rank is equivalent to finding a maximal subtree. But finding the reduced rank is equivalent to what? Finding a maximal sub-garden. Finding a maximal sub-garden. Sub-garden of, say, if this was graph y, of y. So that's another kind of visual way to represent reduced trunk. We also saw the system of complexes last time. Let me draw this z y hat, and then we had s y z. The system of graphs, or more generally, a system of complexes. In this system, you remember, first we start with x, then we consider two maps, which we assume to be inversions, in case of graphs or in case of complexes. And then S was the fiber product of that. And then this is supposed to be, for example, we took the universal covering of x hat is the universal covering of x. More generally, I could take take any x hat with a free action by a group gamma, such that x is isomorphic to the quotient. Is the quotient by this action. So this is a more general situation. If x hat happens to be the universal covering of x, then there is an action of the fundamental group of x on this universal covering. But in general, you could take just any complex, any graph with a free action by some group. This complex doesn't even have to be connected, for example. Could be disconnected. Just any complex, any action, but you assume that the action is free, and you assume that the quotient is x. Then you take this quotient map. So x hat to x. This is the quotient map. If I take, say, a vertex in x, what's the preimage of this vertex? The preimage of this vertex will be exactly one orbit of vertices in x hat. So orbits go to just points, or an orbit of edges here would go to one edge of x. So preimages correspond to orbits. Then we defined, so y hat, z hat, s hat are defined as fiber products of x hat with y, z, and s respectively. This is what I meant by pulling back the whole diagram. You start with the diagram x, y, z, s, and you take this quotient map, x hat to x, and then you pull the whole diagram. This is what I mean by pulling it. Right? You have a question? So, for example, what? Z hat is the fiber product of x hat and z. Yeah.
Are we starting from the previous diagram having s, that y, and x, and creating the hats once again?
Yeah, hats are created by pulling back by this map. You create all the hats by this. So we start with x, y, z, and s.
Forget about the construction of the last time.
This is exactly the construction that I presented last time. Don't forget about it. It's the same thing.
So what is x here? Is it graph or cell complex?
Which one?
X. What is x here?
Again, our main example for the purpose of Hanna-Neumann conjecture is the case when x, y, z, and s are graphs. But then you realize that it can be generalized, and it's a good idea to generalize it. So I'm kind of vaguely saying that it's either a graph or more generally a complex. So either case. It's a general construction for complexes. And you get a system of complexes in general. So once again, you start with any complex x, then you consider immersions from y to x and from z to x. You remember, immersions are those maps that can be extended to coverings. And also it's a good idea to assume that that extension is pi1 injective also. Like y can be extended to a covering y prime of x. It's a good idea, it's a good assumption to assume that the inclusion of y into y prime is pi1 injective. You don't really have to have that property, but it helps having it. So immersions, and then you take the fiber product S, and then you consider any complex with a group action such that the quotient is x. You consider, you let this map be the quotient map, and then out of non-hats you create the hats by pulling back by this map. So to create y hat, you take y and you pull back by this quotient map. To create z hat, you pull back z. To create s hat, you pull back s. And now it should be clear that, so it is clear that that the action, the free action of gamma on x hat, so we are assuming that this action is free, extends or induces free actions of gamma on y hat, z hat, and s hat. Just because say y hat is the fiber product of x hat and y hat and y, and we have a group action on this. Y hat consists of all pairs. It's like subset of the Cartesian product of y with x hat. So the y hat consists of pairs, and we have an action on the first coordinate of that pair. So by acting on the first coordinate, there is an induced action here. Similarly, z hat and s hat admit actions. And moreover, since the preimages of vertices in x under these maps are exactly the orbits, the same thing is going to hold for these preimages. You pick any vertex in y, for example. The preimage of that is exactly an orbit of the group action on this complex. So preimages are exactly orbits. It means that y is exactly the quotient of y hat. So y is the quotient of y hat, z is the quotient of z hat, and s is the quotient of s hat. Those are the quotients. So that gives a group action. And you, going back to the example that I described the last time in terms of graphs, when those are all graphs, then all those maps, for example, this map from y hat to x hat is going to be a leafage. And this holds in general as well. So that's where I need that assumption of pi1 injective. If you assume that y embeds into y hat in a pi1 injective way, then you can actually just generally deduce that this is going to be a leafage. That means that each component of y hat maps injectively into x hat by this map. So you have the picture that I drew. Y hat maps to x hat. This map is not injective, but it is injective when you restrict it to each component. And the group action, so gamma acts on this, it permutes those components. And one of those components I can pick to be, so going back to the case of graphs, or in general as well, one can prove this. So one component, you pick just one component, call it A. The stabilizer in gamma of this component. So for the action of gamma on y hat, the stabilizer happens to be exactly A. Exactly A, the group that we started with. I mean, I'm going back to the example of graphs, right? It's the fundamental group of y. And similarly, the stabilizer of B, similar component for Z. So A is part of this, it's a component here, and B is part of this, it's a component in Z hat. The stabilizer of B would be B. So once again, we define this hat by pulling back by this map. And it's an exercise to check that every square in the system is a fiber product diagram. A product diagram. Yeah.
How can you prove S hat is the fiber product of G hat and Y hat?
By the definition of fiber, it's kind of taking multiple products. So you take this S hat. So what's an element here? There is a projection. You take an element of S hat and you project it here. That element is part of the fiber product. And kind of pulling in this direction, it's like replacing every, say, edge in S by the whole orbit of edges. So that's roughly the idea. So each element in that orbit will also be, but we did the same thing for Y. Each edge in Y we represented by the whole orbit in here. Each element, each edge in Z, the preimage of that in here is the whole orbit of edges. So on those orbits, you pick just one element in that orbit. That corresponds to a pair. One element in this orbit here and one element in this orbit here. So it's an exercise in definitions of the fiber product. Just try down. So remember that all the hats were obtained by pulling back, by taking fiber product kind of in this direction. But each element in that orbit would look exactly like one edge in S. So that's a rough explanation. So let me leave this as an exercise. So it's an exercise in a definition of a fiber product. Yeah.
Are you sure that S hat to Z hat or Y hat are leakages also?
Are what?
Leakages.
Yeah, exactly. So and that follows from what we just said. So consider this diagram: X hat, Y hat, Z hat, S hat. This is a square in this diagram, and by that statement there, this square is a fiber product diagram. So that means that S hat is the fiber product of Y hat and Z hat. Now we claim that the fiber product of leafages are leafages. So this is a leafage. Why is this true? It follows from the fact that the fiber product of two injective maps is injective. So let's give some. If you have some graphs, Z tilde C. So if the two maps are injective. I'm just taking some complex, cell complex here, and here. And I'm assuming that the maps are injective. This is injective, or injective. Then we claim that the fiber product of them, let's call it S hat, S tilde. Their fiber product also, so it means that we have an arrow this way, we have an arrow this way. And I claim that the composition of these two arrows is injective. So in particular, it will imply that this arrow is also injective. So why is this the case? You just follow the definition of fiber product. Take any element in here. For example, if it's a cell complex, pick some vertex in this. So pick some V here. Pick any vertex in S. What is it? It's a pair of vertices, of two vertices here which map to the same, say to the vertex V. So an arbitrary vertex in S would be represented by pair V and V prime, for example. V prime and V double prime, such that V prime is here and V double prime is here. With the condition that V prime and V double prime map to V. But this V prime is unique. This map is injective. There is not exactly one V prime which maps to V. And this V double prime is also unique. There is only one V double prime that maps to V. Therefore, there is only one, exactly one pair in here which maps to V. In general, there is at most one, right? So for each V, there is at most one pair which maps to V here. And that exactly means that the composition of these two arrows is injective. Since the fiber product of injective maps is injective, it implies that the fiber product of leafages is a leafage. You just do exactly the same thing, but you do it separately for each component. You start with a map. You start with a leafage. It is injective on each component. So you take any component here. You take another leafage. It is injective on any component. So pick some component here. And then you take the fiber product of this with that. What is this? You just take all possible components. Make any choice of a component here. Make any choice of a component here. And then take the fiber product of those two. On this picture, so what is this fiber product? It corresponds to this S hat here is isomorphic to what, as we saw last time? You map Z tilde to here, you map Y tilde to here. You can view them as sub-complexes or subgraphs of X hat. And S hat will be exactly the intersection of those images here. So it's the intersection. And more generally for leafages, you do exactly the same thing. You pick some component here, you pick some component here, you map those components to X hat and take their intersection. That intersection is one of the components of S hat. And how many components do we have? We have as many as we have pairs, A, B. So the set of components in S hat corresponds to the Cartesian product of the set of components in Y hat times the set of components in Z hat. So components of S hat correspond exactly to pairs of components in Y hat and Z hat. So, and that's a nice description, and that will essentially lead. You remember the statement of the strengthened Hahn-Neumann conjecture? It involved double cosets. The word double coset pretty much is going to come from this fact that we have kind of Cartesian product in here. Each component of S hat corresponds to a pair. So this is where the word double comes into the picture, if you restate it in more topological terms. Yeah, okay, any other questions? Another notion that I will need is orderability. So we have this nice presentation of hanonomic conjecture due to Stallings. Now we made kind of an equivariant version of it, right? We replaced all the finite graphs with hats, and those hats are infinite graphs. And the idea is to use an additional structure on free groups. And this is called left orderability or orderability. So a group gamma is called left orderable. If there is a total order on gamma, which we denote by less than or equal to. So what's a total order? First you take the definition of partial order, right? It's a relation on pairs of elements, right? You declare for any pair, given a pair of elements, you declare which one of them is bigger, which one of them is larger. So it should be a transitive relation, it should be anti-symmetric, and it should be reflexive. So each element is at most itself. If you have A is at most B and B is at most A, then A must be equal to B. That's the anti-symmetry. And transitivity means that if A is at most B and B is at most C, then A is at most C. So that's a partial order, and you call it total if. So what's the definition? Have you seen the definition? Total means that any two elements are related. So for any two elements, A and B, either A is at most B or B is at most A. So that's what total means. And it's an important condition. Total is important here. There is a total order on gamma, which is also, this word left corresponds to saying that it's invariant under the product, invariant under the left multiplication. That is invariant under left multiplication. So it means that if I pick any elements A, B, and G in gamma, and if A and B are related in this way, if A is at most B, then G times A is at most G times B for any triple of elements in a group. There are surprisingly many groups which are left orderable. And a group is called orderable or bi-orderable. So gamma is orderable or bi-orderable. If there exists again a total order on gamma, again as before, such that which is invariant both on the left and on the right, such that for any A, B, G in gamma, A is at most, B implies GA is at most GB, and AG is at most BG. So it's invariant under the left multiplication and also under the right multiplication. So an easy example would be, so what's the easiest example? Easiest non-trivial example of a left orderable group. Integers, right? The set of integers, Z is orderable. That should be reasonably clear, right? With the addition operation instead of multiplication. Z is orderable. it turns out that free groups are also orderable. Not only left orderable, but actually orderable on both sides. And I should say that in all the arguments that I'm going to present, I only use left orderability. So you don't need the full force of orderability, just one side of it. Z is orderable, so any free group is orderable. I looked in the literature for reference, and the earliest reference I could find was a Russian paper in 1947 by Shimbereva. So she uses some results by Magnus to deduce that free groups are left orderable. So it's quite an old classical result. There is also a paper by Vinogradov in 1949 which proves a more general statement. It says that if you have two, say, orderable groups or left orderable groups, then their free product is also orderable or left orderable. That's a generalization of this because you can represent every free group as a free product of several copies of Z, right? And there are many ways to prove left orderability of free groups. And as Sam pointed out a few days ago, one can explicitly construct an action of a free group on the real line. So here is the statement. So if gamma is a subgroup of the group of homeomorphisms of the real line. So this plus means we only consider homeomorphisms that preserve the orientation of the real line. We don't allow flipping of the line. Consider the set of all homeomorphisms. They form a group under composition. If gamma happens to be a subgroup of this group of homeomorphisms, then it is left orderable. Then gamma is left orderable. Actually, the converse is also true. If gamma is left orderable, with the additional assumption that gamma is countable. If gamma is countable and left orderable, then you can actually realize it as a subgroup of homeomorphisms. Let's quickly prove this statement first. So the idea of proof. This is really neat. The idea is, so you have a group action. So gamma is the subgroup of homeo of R. So that means that gamma acts, there is a gamma action on R. This action is by homeomorphisms. One first attempt one can make is pick some point in R. And you pick two elements in gamma and you want to define which one of them is smaller and which one is bigger. You just look how those two elements act on a given point in R. The problem may be that those 2 points say the same point, it is, say, fixed by the two elements. So you cannot really distinguish the two elements by just looking at one point. If you happen to find an orbit, if you happen to find a point in R such that the orbit, such that gamma acts on the orbit of that point freely, in a free way, if you can find a point for which the stabilizer is trivial in gamma, then you can just use the order, the natural order on real numbers to define the order on gamma. But it's not always the case, right? It might happen that there is no point which has trivial stabilizer in gamma. So we would need to slightly modify this idea. And here is the precise argument. So pick any sequence, the sequence x1, xn, x2, and so on, infinite sequence in R, with the property that this sequence is dense, considered as a set, it's dense, which is dense in R. And then you run a similar construction, like a similar procedure. So given two elements G and H in gamma, you pick the first point x1 and see, apply G and H to that point, and see is the result the same or different. If it's the same, then you consider the point x2 and see, apply the two elements to x2 and see is the result different or not. If it's the same result, you continue. Eventually, hopefully, you will find 2 points. You will find 1 point such that if you apply these two elements to that point, you will get different points. Why is that true? I mean, you need to assume that G and H are different, right? If G and H are the same, then it's easy, right? Both G is at most H and H is at most G. So say and assume G is not equal to H. Since G is not equal to H, so we claim that there is some point here for which applying G and applying H will give a different result. Why? Because if G and H actually coincide on this whole sequence, then they will coincide also on R, just from continuity. This action is by homeomorphisms. It's a continuous action. So there will be some points at which G and H are different. So let I be the smallest number, the smallest index among those satisfying the condition that if you apply G to xi, it is not equal to H applied to xi. You pick the smallest such index. So since they are not equal, but this is a point in the real line, this is a point in the real line. So one of them must be smaller and the other must be bigger. So if G xi is smaller than H xi, then define G to be less than H. If it's the inequality in the opposite direction, then you define it in the opposite direction, right? So depending of which one of these points is bigger or smaller, you declare G and H to be bigger or smaller than from each other. And then there is something to check. So you check that this gives a left invariant. Left invariant total order. On gamma. Yeah.
Is this relation independent of choice of our sequence?
The relation will depend, yeah. It's just the existence, yeah. If you pick a different sequence, you will get a different ordering on the group, yeah, potentially.
Then we have to fix this one sequence and given.
Yeah, for a given sequence, you get some order. For a different sequence, you will get maybe a different order. Yeah, but it's only one that we need, right? So just one order is enough for our purposes. And actually, the converse is also true. If a group is left orderable, and assume that this group is countable, then actually that group is a subgroup of, can be realized as a subgroup of homeomorphisms of the real line. That requires some argument. I will skip the proof. You might try to do this on your own. So it's a characterization of left orderability. Now going back to free groups. So as Sam mentioned a few days ago, one can actually, in order to prove that free groups are left orderable, you can explicitly construct an embedding of any free group into this homeomorphism group. There is a way, and maybe I will just write the construction that he mentioned to me. So you just explicitly, you pick a free group, say the group of two generators, free groups of two generators, F2. So F2 is generated by A and B. A is going to be a homeomorphism like this, of this type. This is a piecewise linear homeomorphism of the interval. This is from 0 to 1 and 0 to 1. And take this like 4/5, and take this point to be 1/5. Piecewise linear, and then you repeat it periodically, like that, and so on. This is 1. And for B, so 1/2, you shift this whole picture by 1/2 to the right, and then shift it up by 1/2. So it's exactly the same picture, just shift it up and to the right by 1/2, and repeat. Call this B. Then it turns out that A and B, consider the group, so A and B belong to the homeomorphisms of the real line. And then you consider the group generated by A and B within this group. Consider all possible compositions of A, B, and their inverses. It turns out that there are no relations, meaning that any word in A, B, and their inverses will give a different homeomorphism. So it's going to be an injective map. There is something to check there, and you use ping-pong lemma to do that. To check that the embedding will be injective. So the free groups have this additional structure. And that is nice because we can use that structure in order to induce an additional structure on those hats in the system of graphs. So recall, gamma acts on X hat freely. And the same thing happens for Y hat, Z hat, S hat. Since it's a free action, what can we say about the orbits of this? So consider EX is the edges of X hat, the set of edges. So in particular, gamma permutes this set of edges. It acts on the set of edges in X hat. The action is simplicial, right? It preserves the structure of the graph. But this is also a free action. And what's the importance of a free action? What can we say about the orbits of this? It's not only free, it's also, it's also co-compact, meaning that the quotient of this, what is the quotient? We know that the quotient of this in a system was X. But X was a finite graph. So this action is not only free, but also co-compact. So this induced action, it's a free action, and also freely and with finite quotients, with finite quotient. So pick some element in here, pick some edge, and consider the orbit of this edge. What can we say about the orbit? Since the action is free, So pick some edge in x hat. What is there is a map going from gamma to this E of x hat, which maps an element G to G of E. So you just translate you fix some element, some edge, and then for each element of gamma you translate that edge by that element. So that's the orbit map. So what can we say about this orbit map? Yeah?
Do you allow gamma to reflect the edges?
We assume that the edges are assumed to be oriented, like in a Cayley graph. In a Cayley graph, so we do not allow the action should preserve orientation. And you can check that for the Cayley graph. So start with any group, consider its Cayley graph with respect to some finite generating set. You remember I made a direction from each edge in a Cayley graph is directed. There is an orientation on the edge. One can check that the group acts on the Cayley graph, and that action preserves orientation of edges. So I will always assume that, yeah, there is an orientation, and this orientation is preserved by all the actions considered. Yeah. So what can we say about this orbit map? From the fact that the action is free. Since the action is free, it means that the stabilizer of this edge in particular must be trivial. That's equivalent to saying that if you have a non-trivial element of the group, then G times E will be different from E, must be different from E. So any non-trivial element the image of this will be different from the original edge. And that essentially means that this orbit map is injective. So the fact that the action is free implies that this map is injective. Injective, and also what's the image of this map? The image of this map is exactly the whole orbit of E. So in other words, this map here gives a bijection between the group and the orbit. This proves the following, that each orbit, gamma orbit, in the set of edges can be viewed as a copy of gamma, just as a set. There is a bijection between gamma and this set, is a copy of gamma. So we have this group action on this set, and how many orbits do we have? So this condition with finite quotient, right? Finite quotient means that for this action there are finitely many orbits. Copy, and there are finitely many orbits. So that means that then we can identify the set of edges with, so it's just finitely many orbits, but each orbit is a copy of gamma. So it's like a disjoint union of several copies of gamma. We can represent this as gamma cross the Cartesian product of gamma cross some finite set. A finite set. But now, what is gamma? Gamma is this group. You remember, it was a free group. In particular, it is left orderable. So there is an ordering on gamma here. There is a total ordering on gamma, which is invariant under the group. And this is just some finite set. So we can put some ordering on it as well. So put some total order on the set, on this set. So this also has some order. And the set of edges is is a copy of this Cartesian product. This is an ordered set. This is an ordered set. Then a Cartesian product of two ordered set also can be viewed as an ordered set. So what's the way to put an ordering on the Cartesian product if you have an ordering on each component? That's called, you know the name? Lexicographic order, right? Put the or A. There are two ways to choose lexicographic order, right? Depending if you write like in from right to left or from left to right, depending on how you organize the dictionary, right? Yeah, I will say the order, lexicographic order. Order on this product, which means on this set of edges. So what's important, either one of those. What's important is that this lexicographic order, recall now, we have a group action here. So in particular, we have a group action on this set. And one can explicitly say what the group action is. So if you represent an edge here as a pair, an element of gamma times some element of this set. So how do you act on that pair? By some element of the group. It's just the action on the left. This action on the whole set is equivalent to acting on the set of pairs like this, just by acting on the first component. So there is a gamma action on this, and one can check that this order is gamma invariant. So that was the whole point, yeah.
The finite set is just the set of the x, right? The edges of x.
Yeah, you could identify the finite set with the set of edges in x. Yeah, it's you can identify it with the quotient. Or another way would be to consider all the orbits for this action. And in each orbit you pick a representative. That of course gives a bijectively equivalent set. So like, say, maybe a convenient way of thinking of this, you pick a fundamental domain for this action. But that fundamental domain one-to-one corresponds to edges in X. Yeah.
How does finite set can be gamma invariant?
Can be what?
I don't think finite set can be gamma invariant.
So just
can be what?
Gamma invariant.
Gamma invariant. It is invariant just by definition, pretty much. You construct this isomorphism, this bijection, in such a way so that the action, the gamma action on here corresponds to the left gamma action on this set. By acting just on the left component. There is a way to construct this bijection in such a way. And that means that since the action is only on the left component, it means that we consider the action of gamma on the right component to be the trivial action. The action which doesn't move anything. It's the action by the trivial group.
So basically you're ordering all the edges of the infinite tree.
Yeah. Yeah. So if this is a Cayley graph, right, for example, the group gamma acts on this Cayley graph for F2, say, right? There are two orbits of edges. And we just, one orbit corresponds to gamma, there is an ordering on that. Another orbit corresponds to a copy of gamma. There is an ordering on that. And we kind of interpolate those. You extend this to an ordering of on the whole set of edges, on both. And this is the trick to do it. You identify the union of two orbits with gamma cross the set of two elements. Yeah, you have a question? Yeah, so that was the point. We put a gamma invariant, and it's a total order. Maybe I should say this is the total. This order is total, just by definition of lexicographic order. Any two words are related. So what's the lexicographic order? Say you have a pair A, B, and then you have a pair A prime, B prime, right? Suppose you orient them, order them in like in a dictionary. So if A prime happens to be bigger than A, then you declare what? Then you declare this pair to be bigger than this pair. If A and A prime are the same, then what? Then you have to look further. Then you see, is B prime bigger than B? If B prime is bigger than B, then you declare this pair to be bigger than this pair. If they are the same, of course, then the two pairs are the same. So that's the definition. And after we have this gamma invariant order, so what's the idea of proving the Hahn-Neumann conjecture? You remember we want to show that the reduced rank of S is at most the reduced rank of Y times the reduced rank of Z. That is the goal. And we saw a way to represent the reduced rank of some graph. Say, what's the reduced rank of Y? That's the same thing as the number of edges in some maximal essential set of Y. The same thing for this. If you pick some maximal essential set for Z, the reduced rank is the number of edges in that maximal essential set. The same thing for S. So we can restate the question in terms of reduced ranks in terms of now of edges, of picking some set of edges in Y, some set of edges in Z, and some set of edges in S. The question is, how do you pick them, those sets consistently? And this ordering here. So we just put an ordering on X hat. The next step will be to put some ordering on Y hat, on Z hat, and on S hat using this. And see that it's a consistent way of putting an order. And then we will use that ordering to find, in some nice way, a maximal essential set in Y, a maximal essential set in Z, and in S, which would make this equality hold. So that's the idea. Use the ordering to pick maximal essential sets. So going back to the system of graphs, now we have an ordering on the edges of X hat. Y hat, X hat. So part of that diagram was Z hat and S hat. So we have an ordering here now. Now we want to put an order on Y hat. And there are kind of two options. You either really require the ordering on the edges of Y hat to be total, or you take a slightly weaker condition. So if you really want to induce a total order on the edges of Y hat, then so you pick some edges, say E and E prime in Y hat. You want to declare which one of them is bigger, which one of them is smaller. You might look first at their images in here and see. For example, it happens that the image of E in here is bigger than the image of E prime. Then it's natural to declare that E should be bigger than E prime. That's how we define it, right? What if not? What if the images actually have the same? If these two edges have the same images? Then it means that they lie in the preimage of some edge in here. So this is called a fiber, right? You have some edge in here, and the preimage of this edge is a fiber. The fiber consists of finitely many edges. And this E and E prime lie in the same fiber. But then you can put some order on the fiber. So in other words, that's kind of roughly the same trick as we did here, right? Since we already have an ordering on x hat, you can realize the set of edges in y hat as x hat, like in the horizontal direction, times the fibers. Except that the fibers might be different, right? You cannot really write it as a Cartesian product anymore. But roughly the same thing happens. For different edges, fibers might be different. But there is pretty much exactly the same way to put a lexicographic order on y prime, which is consistent with the ordering in x hat. So let me put it in parentheses, lexicographic order. Lexicographic order on y hat using the order on x hat. So that way we'll give you a total order on the edges. Maybe I should say not on y hat, but rather on the edges of y hat. This gives a total order on the set of edges. Alternatively, one can just recall that this is a leafage. And leafage means that on each component this map is injective. So we can just put an order on each component separately. We don't, yeah?
Do we arbitrarily give an order to each fiber?
Order to, yeah, we put an order on each fiber just as we did here. We put some order on a finite set.
Doesn't that necessarily be finite? Doesn't each fiber necessarily be finite?
It is finite, even though it's not really important, but yes, it's going to be finite in this case. The reason is that the quotient of y hat by the group is a finite graph. The quotient of x hat by the group is also a finite graph, x and y. So the fibers of this map are exactly the same as the fibers of the map y to x.
Which is fine.
And these fibers, they are all finite. So yeah, even though for the definition, of course, it doesn't really matter. On say,
I think x is typo.
This one?
EX.
Oh yeah, maybe I should say I'm kind of being sloppy here. Yeah, on the set of edges of x hat. Yeah, that's right. That's what I mean by an order on x hat. The order on the set of edges. Yeah, so this is a way to put a total order, or we just don't require the order to be total. We just take any component of y hat. So alternatively, put the order on each. Let's see, on say E of k, where for each component k of y hat. So this order, how do we put it? Take any component of y hat. That component maps injectively into x hat. So since x hat already has an order, the set of edges, then on that component is just a part. You can view this as part of this, of x hat. So you just restrict the order from x hat to that to only that component, and you do it for each component separately. So this gives you an order on the edges of each component, but maybe not necessarily an order on the whole y hat. But still, that will be good enough for our purposes. All we care really is about are the components.
Can you put an order of the components and then use?
That's troublesome because I want the ordering to be invariant under the group. So one needs to be careful. I mean, it's not immediately clear that any order on components, together with the order on each component, would give you a total order which is invariant under the group. So this lexicographic construction gives such an ordering. If you do it in a different way, I mean, one needs to do it carefully to make sure that the resulting order is invariant. We can do the same thing for z hat. So do the same for z hat and s hat. So again, we have an ordering on each component of y hat. We have an ordering on each component of z hat and also on each component of s hat. But what is this? If I pick one component here, one component here, a component of s hat corresponds to pairs of such components. And that component is exactly the intersection of the two, right? And all we did, we just took the order on x hat and we kept restricting it to smaller and smaller. First we restricted it to a component of y hat, then we restricted it to a component of z hat, and then we restricted to their intersection. So those three orders that we put, they are consistent. So the orders on y hat, z hat, s hat. First of all, they are gamma invariant and consistent on the components. And now it's a good time to stop. Now do as an exercise, use this to prove Hahn-Neumann conjecture, and we'll talk about it next time.
Gamma action on y hat and z hat are component-wise. So
not quite. I mean, the gamma action permutes components of y hat. But then you can only restrict your attention to the action of the stabilizer. So pick some component of y hat and consider its stabilizer, which is A. That action preserves the order on that component. And that's pretty much the only thing we need. Yeah. Thank you.